What is Kubernetes? Why it's called K8s and what makes it so popular? Let's find out. The name Kubernetes originates from Greek and means chaosman or pilot. Kubernetes is a container orchestration platform. It automates the deployment, scaling and management of containerized applications. Its roots lead to a tool called Borg, developed by Google. Most of the features in Kubernetes originate from Borg, and with Kubernetes the Google developers aimed to learn from their mistakes and improve on the next design. Kubernetes is currently one of the biggest open source projects by the number of commits, authors and issues. And the number 8 in K8s refers to the 8 letters between the first letter K and the last letter S, similarly to the word internationalization. But why would someone want a platform to orchestrate containers? After all you need is a place to run your containers, like a server or a virtual machine, and a container daemon like Docker. Then you can start your containers and that's it, right? Well, no, or at least it depends. How are you going to scale your containers if the load of your application increases? Is this process automated and dynamic, or you should run more containers manually? Can you seamlessly route or load balance traffic to multiple containers? What will happen if your server fails? Can you easily replace it? Or if the application in the container crashes? Do you stop your application to do an update? And what happens if the update fails? Can you easily roll back to the previous state? And this is where Kubernetes comes to play. With Kubernetes you can say, I want 3 containers hosting my WordPress application. And Kubernetes will make sure you always have 3 containers ready and serving traffic. If there are suddenly less than 3 containers, Kubernetes will launch a new container to maintain the quantity. Kubernetes will also monitor the status of your servers. And if a server fails, it will reschedule all of its containers on the rest of the nodes. In Kubernetes, the containerized applications run in so-called pods. The pods are the smallest deployable compute units. A pod consists of one or more containers and provides shared storage and networking between them. The hosts that are used to run those pods are called worker nodes. The worker nodes are the first piece of a Kubernetes cluster. The second one is the control plane. The control plane is responsible for managing the cluster. In production environments, the control plane usually spans across multiple nodes placed in several availability zones. But let's have a better look at the worker nodes. Each worker node has a daemon called kubelet. It is responsible for registering the node in the control plane. It also receives instructions from the control plane about which pods to run on the node. The container runtime runs the containers on the worker nodes. It is responsible for pulling the container images from a container registry, starting and stopping the containers and managing their resources. The kubeproxy is a network proxy that runs on each worker node. It is responsible for routing traffic to the correct pods. It also provides load balancing for the pods and ensures traffic is distributed evenly across them. The worker nodes, the pods, all other Kubernetes resources and the cluster state need to be managed. And here the Kubernetes control plane comes to play. It consists of a number of components. The scheduler selects on which worker node to run the pods. The selection is based on different criteria like CPU and memory utilization, or a set of predefined rules like node affinity. etcd is a consistent and highly available key value store. It is used as a Kubernetes backing store for all cluster data. The controller manager watches the state of the cluster and makes changes where needed. There are multiple controllers in the controller manager. Each controller tries to move the current cluster state to the desired state. The controllers act like a thermostat. The thermostat turns on or off the AC to make the current temperature match the desired temperature. It's just that Kubernetes uses YAML files instead of a knob. A sample of a controller would be the deployment controller, responsible for bringing up the desired number of pods in a deployment, or the replication controller, responsible for keeping the pod replica in a stateful set. We'll see what a deployment and a stateful set are later on. The Cloud Controller Manager is an optional component used to talk to different cloud providers. It allows easier interaction with the cloud providers using a plugin system. The API server is the interface between the control plane and the worker nodes. It also exposes an API that allows interaction with the cluster. Let's check out the API server in more details. Using the API server, we can create a deployment in Kubernetes which will start 3 identical pods. Also, we can create a stateful set in which each pod will have its own state stored on disk. We can also expose those newly created pods to the outer world using a service. And there is no need to manage load balancers. Kubernetes contains built-in load balancing based on the service concept. There is also integration with the cloud provider's load balancers, which is actually one of the most valuable options for exposing a service. Let's see how that works in practice. First, we will install local test Kubernetes environment with Minikube. Then we will start our Minikube cluster. Let's now check if there are any pods running in our newly created cluster. There are no pods running as we have not deployed anything. We can now apply our deployment config, which will bring up 3 pods containing Nginx. We can check them out. They have been already started and are in a running state. In order to emulate a load balancer in our Minikube Kubernetes cluster, we will start a tunnel. Now let's create a service of type load balancer, which will expose access to our Nginx pods. The service should be accessible at our computer's localhost at the defined port, which is 8080. Let's check that using CURL. We can see the response from the Nginx pods. At the end, what are the pros and cons of using Kubernetes? Kubernetes is scalable and highly available. Features like self-healing, load balancing and fault tolerance are all automatic once configured properly. Kubernetes is portable. It allows managing applications in a consistent and reliable way, regardless of the used infrastructure, and whether it is on-premise, in the cloud or in a hybrid environment. Kubernetes continuous update strategy avoids application downtime by keeping some of the old pod instances running, while new pods are being provisioned. When the new pods are ready to handle traffic, the system activates them first and only then shuts down the old ones. On the other side, deploying an application in Kubernetes can be easy, but managing it has a lot of caveats and a steep learning curve. Hosting Kubernetes has its administrative overhead, and the cloud-based versions cost a lot of money. Don't forget that with Kubernetes your hosting bill will also scale. Kubernetes requires some server resources to run its own processes, both for the control plane and for the worker nodes. Finally, when to use Kubernetes? You need a container orchestrator when you have a productive microservice-based application, composed of multiple services, which are themselves composed of containers. Having Kubernetes to run a monolithic application would be an overkill. And why would someone need to scale an application frontend if the backend or the database becomes a bottleneck? And do you really need 500,000 additional lines of code just to manage your application better? The bottom line is, you should choose your battles, plan wisely according to your use case, and be well prepared for what comes next. Deploying an application in Kubernetes is easy, but managing it effectively afterwards becomes the tricky part. As usual, the devil is in the details. Thanks for watching. Are you using Kubernetes in your daily tasks? Please share in the comments your view on the topic.